Olá pessoal. Um, I will do English because for the future and because we have Erasmus students as well. So this class will be part of the simulation of technological processes YouTube channel. So I will send you a link for the channel and for this video on the Teams platform we have. So basically this part of the theoretical content is basically what you need in terms of subtract to understand and justify the differences of results you will have with the assignment you are doing. The first assignment where you have a simple linear elastic example. You are going to perform simulations on Abacus with different meshes and different finite elements. Differences will arise, and so with this we'll show you how the software has some different solution types for different types of problems, and you see how some of them adapt or not to the problem you are monitoring, either in terms of displacements and stresses and so on. So basically during the years engineers were being faced with different challenges in terms of simulation of new materials, new processes, either metal forming or composites or whatever you may think about it. So every time engineering evolves and new process, new products, new materials, software needs to keep the pace and try to be as accurate and as efficient as possible. So when you think about the standard finite elements you see on the books, you will see that they didn't work well for a wide range of problems, and because of that it's necessary to create new improved finite element formulations. So we are now going to discuss some of the problems that may arise. So just so you have an idea, one of the concepts we are going to address here, the reduced integration concept that applies to 2D, to shell, to 3D elements, was first applied in 1970, so long time ago. Another one that we are going to also see today on Abacus as well is the incompatible modes method. So it's the C3D8I, okay? So the reduced integration is the C3D8R element that we are going to address. And in 1978, what we call the selective reduced integration, that is basically the C3D8 standard element. So as you can see, the standard Abacus element is not really standard when compared to the books. It's the selective reduced integration. And so things evolved, and until today you can see people publishing in this area. So let's start to see what can go wrong when you use finite elements. And the first one is the incompressibility issue that can happen in two different situations. First one is when we deal with an incompressible material. Incompressibility in the linear elastic regime is given by the Poisson coefficient equal to 0.5. You see this Poisson coefficient, for instance, in rubber-like materials. But when you leave elasticity, when you go into plasticity of the metals, for instance, if you are doing some metal forming, press forming, forging, rolling, any kind of metal forming process, and when you go into plasticity, plasticity happens in constant volume. So that means we have also incompressibility when you have plastic deformation. So most of technological process to deform materials. So when you have these conditions, there is a problem called locking. okay? So, and in this case, because of incompressibility, that means constant volume, so it's the volumetric locking. So basically, the condition to have incompressibility, when you think about your stress tensor, if you consider the volumetric component, so the epsilon xx, yy, and zz, so if you think about the strain tensor, the diagonal of the strain tensor, so if you sum up this diagonal, that should give you, according to solid mechanics, the variation of the volume. So when you have incompressibility, this must be 0, okay? So basically, if you think about what we call the bulk modulus, that is basically the division between the hydrostatic pressure and the variation of the volume, what happens when this goes to 0, or in terms of Young modulus and Poisson coefficient, when this goes to 0.5, you have a 0 on the denominator. So that means the bulk modulus will go to infinite, okay? So if you remember about solid mechanics, there were two different ways to express Hooke's law in elasticity, or using the Young modulus and Poisson coefficient, but also using these two Lamé parameters, where this new parameter is basically the shear modulus. But it's interesting to see what happens here on the lambda coefficient, because since the Poisson goes to 0.5, this parameter also goes to infinite. So if we express Hooke's law using the Lamé parameters, what you are going to see is that if under incompressibility lambda goes to infinite, then the whole stress goes to infinite. With that, we must return to the definition of our stiffness matrix. So if you see, the constitutive law is basically the derivative, first order one, of stress to strain. So if stresses goes to infinite, or if you derivate this in order to the strain, you have this lambda, and lambda goes to infinite. So that means the whole stiffness matrix goes to infinite. So in finite element methodology, we determine the displacements inverting the stiffness matrix of the problem and multiplying by the force. So if the stiffness goes to infinite, the inverse naturally will go to 0. So no matter how big these forces are, your displacement will be 0. Okay, so this is the classical mathematical definition of the volumetric locking. Okay, you can see it also visually. So everyone is seeing this node A, okay? This is an area, okay? So under incompressibility, the element 1 and element 2 must keep the area, the original area. So if you think on this node, let's imagine this node can move on horizontal or vertical direction. So it's a 2D problem, 2 degrees of freedom, but will never move. Why? Because if you try to push this node on the horizontal direction, you see that the area of both elements 1 and 2 will be changed. And if you try also to move the node on the vertical direction, that will imply as well a change on the area of the two elements. So we are violating the constant area or incompressibility in this case. So it's more visual here and more mathematical here. But anyways, basically incompressibility forces the locking, and the locking is when stiffness goes to infinite and displacement goes to 0. Okay, so let's focus now our study of volumetric locking on the first order brick element, the 8 node brick element. So we are using this element more often in our course. So this 8 node element has 2 degrees of freedom per node, which give us 24 degrees of freedom in the total of the single finite element. We are considering the isoparametric version of the element. So we have a 2 by 2 by 2 cube. We have the natural coordinates here in the center, just like in the basics of finite elements. So what do we know? If you have 24 degrees of freedom, we have a space of solutions that must be 24, because it's the number of degrees of freedom. So we must consider that when we apply a restriction, a constraint, like, okay, I just want incompressible deformation patterns, not all of them. So that must be a smaller space compared to this bigger one that is all possible solutions. What we can state here is that the performance of a finite element is better the bigger the space of solutions of an element. So we need to check what happens to the finite elements we know when we try to impose incompressibility. Okay, so every finite element has a different way to give us the space of admissible solutions and the subspace of incompressible solutions. So the bigger, the better. And I will start with the solution, okay, to justify why the standard is not so good. So the successful solution to avoid volumetric locking is doing the reduced integration. So as we discussed in the last class, the standard integration is a 2 by 2 by 2 with 8 integration points to integrate the stiffness matrix, but we can use the reduced integration that only integrates in the center, okay, in the coordinates 0, 0, 0. So what we are going to do is to check how good this element perform under incompressibility. We are going to discuss also the problems that under integrating the element, as we are doing here, may rise. So one of these problems that will arise is the hourglass. So the stiffness is under-evaluated and the element becomes too flexible, okay? But let's see why it's successful solving volumetric locking. I'll come back here. First of all, we will define the subspace of incompressible solutions. Remember that incompressibility is given when our volumetric strains summed up must be 0. So substituting this expression by the interpolation using shape functions, we have this expression, okay? Obviously, this equation is satisfied when the displacements for all the nodes in all degrees of freedom is 0, but we don't want this solution. This is not a solution. So let's find a patterns or different patterns of displacements for all the nodes where this condition is satisfied. So it's like we are trying to teach a robot how to move. So for instance, these movements could be moving a leg, moving an arm, bending over, kneeing down. So different combinations. So the more combinations of displacements and deformation patterns we can have here, the best is the element reproducing incompressible deformations. In the case of the reduced integrated element, we find that 23 independent different deformation modes can be done under constant volume, under incompressibility, okay? So combining up these 23 different deformation fields, we can reproduce a lot of different ways of the element deforming, okay? So these 23 different deformation modes are very simple. See, axis or edges translation, you see that the volume is constant because diminishes here and goes up here. The same over y and z direction. So in total is 4 edges translation in each axis, so that goes for 12 different modes. Then we add up with 5 deformation modes where we have one of the faces compressing and stretching in the perpendicular direction. That gives us in 5 faces, because the sixth one will be dependent, so can be obtained combining the other 5. And finally, 3 trapezoidal. Okay, see, volume constant, so we can make 3 different combinations without being completely independent of each other. And finally, what we call non-physical, because it's like the face is being twisted, but even so keeping the constant volume. So these are 23 different modes. So this is what is considered the best performance of a finite element, the brick element at least, version of it, with 8 nodes under volumetric locking. Now let's talk about what happens. I'm come back here. Yeah, the slides could have a different order. Anyways. So, sorry, some interruption here. Okay, the reduced integrate element avoids volumetric locking, but what happens when I switch from 1 point in the center to 8 points? So the fully integrated element, as you see in the books. So from the 23 deformation patterns that you can get with reduced integration, only 17 can be done using volumetric locking, using the fully integrated element. So if you try to reproduce these deformation modes, you are going to have a 0 displacements, okay? So it's impossible. So that's why the standard finite element suffers from volumetric locking, okay? Now I'm coming back here to explain the downside of reduced integration elements. So we are under-evaluating the stiffness of the element. So what you're going to see is sometimes you can have a deformation energy without any displacement. So there's something called hourglass patterns. Some of your colleagues already experienced on the first class of the last week, but you can easily detect when you see this kind of trapezoid shape. So if you look to these elements, they make a kind of a hourglass pattern. So you have to imagine here a hourglass. So, and this is also called spurious deformation modes because it's deformation with no energy, but you can see a lot of displacements. Okay, a visual example can be seen here. So you have an integration point on the center of the finite element. The element is being bent, so you should have here compression on this face and stretch on this one, but because the integration point is in the neutral line, you don't detect at all any deformation. Okay, so no strain is detected, but you have deformation energy, right? So this is the problem that happens when you have a reduced integrated element. Okay, so once again, this is the formulation in Abacus known as the C3D8R. Okay, the R is standing from reduced integrated. So you'll see when we are going to use Abacus that there are some options to control the hourglass instability. Okay, so we are going to discuss this on the practical side of our classes, okay? So this is the C3D8R element. So you will also see that the C3D8 from Abacus is also locking free. So the C3D8 is not actually the standard finite element you see on the books. There are some tricks. So there's no hourglass problems in C3D8. So why? Because in the C3D8 element, instead of using reduced integrate scheme on the whole element, we are going to use what we call the selective reduced integration. So if you recall solid mechanics, you will remember that we have the deviatoric and dilatational, or in Portuguese, hidrostático e de desvio. So we separated the volumetric part, or dilatational or hydrostatic, and the deviatoric part of the stress and strain tensor. So with that we can construct stiffness deviatoric and stiffness dilatational. Volumetric locking comes directly on the volumetric dilatational or hydrostatic part of the stiffness. So basically what we are doing here, instead of using reduced integration on the whole stiffness, we are using reduced integration only on the hydrostatic part, okay? And we are keeping the deviatoric part fully integrated. So the element is semi-reduced in terms of integration, not completely, like the C3D8R. And with that, you can avoid the volumetric locking, okay? But you don't suffer from hourglass phenomenon, okay? So bottom line, not as fast, because the C3D8R is doing calculation on just one integration point instead of 8, but is way more stable, okay? So now there is a question. So if I don't want to use any kind of a reduced integrated scheme, even complete or selective, like we saw, is it possible to avoid volumetric locking by reproducing the 23 deformation patterns we discussed some slides ago? Well, the answer is yes. So there are two very similar methods, the incompatible modes from 1973 and the enhanced strain method from 1990. Both of them there are some slight difference that we are not going to discuss here, but you see this in Abacus as the C3D8I, where I comes from the incompatible modes, okay? So instead of doing a reduced integrating scheme to make the element softer and more flexible, we are keeping full integration, but we are adding a new deformation vector. So instead of having only the displacement strain operator, we are going to create a new one. And with this new strain displacement operator, we are going to create a new set of variables. And with that, we are going to have the enhanced strains. So if we imagine that the standard element reproduces 17 deformation patterns and the reduced integrated produces 23, that means that these 6 deformation patterns that are not present on the standard deformation will be obtained using the enhanced deformation. So this is the basic idea. So we are going to develop or to choose proper new deformation patterns. So these are called the incompatible modes. So this element is way slower because we have full integration and now we have more variables. So we have 24 degrees of freedom and now we are adding more degrees of freedom. Okay, and things got way more computationally expensive if you consider how we get the final stiffness matrix. So now, instead of only calculating the typical stiffness matrix, you need to condensate these other three components and do inversion and so on. So this is a real bit advanced for this part of the course. So it's more going for PhD or postgrad. But anyway, just so you have an idea of the computational effort that you must put when you go for this kind of method. Anyway, the results are very nice. So this is basically the 6 degrees of freedom that are added. So that means we are going to create here a matrix that I'm calling M there, but with 6 degrees of freedom additional. So that corresponds to 6 new columns on this new strain displacement operator, and you see that they are acting on the volumetric lines of the strain vector, so xx, yy, zz, or eta eta, xi xi, eta eta, and zeta zeta. So this is volumetric part. So with that, we will check on Abacus how these elements will behave in terms of volumetric locking, which is very obvious on the first assignment, that is a cube under compression. And now let's do another thing that can go wrong when you use the standard finite elements to simulate, and this happens when you have a sheet modeling. So we have a low values of thickness, and that induces another kind of locking that is not related as the previous one to the incompressibility. So we can have a linear elasticity with a Poisson coefficient of 0.3. That's the typical of metal materials. But we have a different kind of locking that's called the transverse shear locking. So there is a condition that we can express mathematically, and we can also check it more visually. So, but basically what we need to fulfill when we are dealing with a shell element is our transverse strain energy must be 0 to reproduce the so-called Kirchhoff-Coiter conditions. So translating this into something more meaningful for you, so we can have a comparison between the shear. So we have a bending here, so we have a pure bending, but we can check what happened with a linear element and a quadratic element. So when you have pure bending, you can see that the quadratic element can reproduce well the curvature, but with the linear element, what's going to happen, because we cannot have here a curve, because the natural linearity of this kind of elements, we are not going to fulfill the condition. So you can see here that the edges are unable to curve, and so we are going to have a shear deformation that's artificially created. And because this shear is created, our stiffness go up, and because there is over-evaluated, the displacements will be lower than what you should expect in this kind of problem. So the deflections will be smaller. So the element basically becomes too stiff because we are creating what we call parasitic strains that will lead to parasitic stresses. So yeah, visually you can see so what happens when you have a shear locking. All right, so this is a characteristic of a linear element. Okay, so first order elements like we have, for instance, on the C3D8. So yeah, one way to solve this is to use the quadratic elements, but as you know, quadratic elements will bring another type of problems, or at least you can think about the computational efficiency will be way worse compared to first order elements. Once again, the solution for transverse shear locking is to use reduced integration. Here, this is represented by the shell element. So you have here the fully integrated shell element. So the shell element is like a 2D, but you can have a 3D behavior by having 3 degrees of freedom for every node, so X, Y, and Z, plus rotation on the node. So we are also still going to address this on the classes. So we have here the fully integrated version of the 4-node shell and the reduced integrated version. And then we are basically going to do the same methodology we did for volumetric locking. So we are trying to find, with the reduced integration element, how many different deformation patterns I can find using the reduced integration. So this is the work of actually our head of department, Robert Valent. So he was able to find 10 different deformation patterns that would fulfill this condition we defined it right here on the first slide. Okay, 10. So if you remember volumetric locking, that was 23, here it's 10. So not easy to visualize because it involves rotations, not only translations, so quite difficult to visualize here. Anyway, just to let you know that if you use the full integration on this element instead of reduced, only 4 from the 10 define it. So once again, we need to either or use the reduced integration or use the enhanced strengths like we did for the volumetric locking alleviation. So once again, we are going to create a new strain displacement operator and once again create new variables. The difference here is, if you recall what we did for the volumetric locking, we performed we did some enhancements on the volumetric components of the strain tensor, so the 3 first lines. Now we are going to act on the shear components of the strain. This is the in-plane strains. This is a transverse strains. So that's why we are just going to use the 5th and the 6th line that are for the transverse strains. So what I'm telling, this is XY. If you think about the strain tensor, this is XZ and YZ. So out of plane deformations. Okay. So yeah, that will give you basically what I element like the C3D8I has. So I element like the C3D8I is what we call a solid shell. Well, it's not so good as the one I'm going to present, but the concept is the same. So basically we are going to have a solid element fully integrated, okay, but that is capable of performing well under incompressibility and under low thickness problems, okay. There is some advantages compared to shell elements because shell elements, they have no thickness, and solids, you have a thickness, okay. So with that you can use full 3D material laws, so no need to use plane stress assumptions. Strain variations are very easy to detect because you have physical nodes here instead of shells that you have no nodes over thickness, and it's easier to model double contact. That is, we need to use when you do sheet metal forming simulation. So yeah, this is an element I developed with actually Professor Hubbard some ages ago, and this is a incompatible modes element, and we are here solving the volumetric locking on the volumetric components, and here solving the transverse shear locking here. Okay, so that means we are applying extra 12 degrees of freedom. So this element has 24 from the standard part plus 12 variables, so meaning it's 36 in total. So computationally speaking, is not very efficient, but it works well. So let's see some examples. So this is the NUMI sheet conference 96. So it's very old. Even myself, I was still studying during this time. So I showed this on the first class. So the challenge here was to detect the wrinkling pattern here. And we basically, when we go to this conference, you compare your simulation, in this case in terms of a punch force and punch height, against other solutions. So you can see this is some softwares from other companies or other universities. So our solution, our proposal was more or less in the average. This is something that we're still going to talk about on these classes. So implicit and explicit versions of finite element codes. But of course, if you think about the computational time, you can see that C38 take 8 hours. The C38R should be faster because it's reduced integration, but it takes more iterations on the nonlinear analysis. So we are also still going to discuss the nonlinear algorithms, but it needs more iterations to get convergency. So it gets more 5 hours, which is impressive. So the C38I that is based on the incompatible modes is the slowest, and the present is 36, but it was implemented as a Fortran code outside Abacus, so it's not optimized for our user element. Anyway, the results were good. So yeah, so this element has been used for different simulations with success. Actually, this is one of your last assignments that is performing hydroforming composites. And yeah, the element could be better. Okay, so I'm finishing because it's getting longer. I'm finishing here, but yeah, one day with time I will speak about this another solid shell that is not on Abacus, is present on other codes, namely the MSc, Mark, and Astran. So this was my PhD work, and it's an element that can perform very well but has